Welcome back to ECE 340. The next time we're in this classroom, you will be in the test mode. Maybe we'll have a few more students present on that day. Just an announcement, there are some opportunities for summer research, and those are on the news page of D2L or on the front page of this class website for D2L. Homework number 5 is due today. Exam 2 is Thursday, and there's a review session tonight in room ECE 530 beginning at 5:15. What I want to do today is simply state the process for exam number 2. That should be consistent with exam number 1 as far as the procedures that we'll follow, and we'll then pick up with Bode plots where we left off with linear factors. We'll talk about complex factors, the two sort of extreme cases for complex factors, and then how we will go ahead and approximate those complex factors. That's sort of our inside agreement for this class, is we will simply approximate these complex roots as if they were two real equal roots and make those sketches. That's not really what you will see, and we'll discuss the variation between the two extreme cases, and then depending on your zeta value or damping ratio, that will influence where you live relative to those two extreme conditions. The process for exam 2, 2 sheets of notes, and that will be front and back of an 8.5 by 11 inch piece of paper. If you want the Laplace transform tables, bring that with you. That won't be furnished, but you will be allowed to have that as a third piece of paper on your desk. That's table 4.1. Those are the one-sided Laplace transforms. That's what we're assuming here, that t equals 0 is where we start, and then we go for non-negative values of time. That's what's called the unilateral Laplace transform. You can bring a calculator and something to write with. Questions on that? Yes? If you want a more extensive Laplace transform table, try to incorporate that into your 2 pages of notes. You can put whatever you want on your 2 pages of notes, and if you want more transforms, that's up to you. Other questions? Yes? At the bottom of table 4.1, they have, I think it's row 10, but there's 4 different ways of doing complex roots. This table I've also made available to you on D2L in the exam 2 section, but you just need to get familiar with one of those. It's 10A, 10B, 10C, or 10D. You figure out which one you like, and I would just stick with that one if I were you. But they're all equivalent. So if you like, excuse me, to use 10D, then use 10D. If you like to use row 10A when you're dealing with complex roots, use row 10A in that table. They're all equivalent, and you can show that they are equivalent to each other, and so you shouldn't have to. Is that what you were asking about? No, you can. That's basically then converting between a sum and or a linear combination of sines and cosines that are damped at the same amount of damping, and they have exactly the same damped frequency of oscillation. You can linearly combine sines and cosines, and that's what they're doing with those formulas in those rows of that table. If you like to keep them separated, that's fine also. And I think in one of the solutions to an earlier exam, I go through different ways of dealing with complex roots in an inverse Laplace transform, and you might just look and see which of those you like or which of those you feel more comfortable with. Getting back to where we left off last time, we were talking about Bode plots, and you've had to do this, so hopefully this is really sort of a review for you, but maybe it will become even more clear after today's material, dealing with linear factors, which is this s plus something. And typically we write that in time constant form where we normalize that constant coefficient to have a value of 1. If you then identify what it is that's multiplying your s with this denominator variable, that's where your pole is located, or we were calling it last time, that's where we break in terms of our Bode plot. That's our break frequency. If we had a pole at s equal minus p, which you can see that's the value of s that causes this denominator to vanish, that's by definition the pole. Then when you go into the frequency response, which is obtained by letting s be equal to j omega, we might call that p the break frequency omega naught. And that might be at 5, it might be at 1.7, it might be at 0.26. Yes? So when we're calling that the break frequency on the Bode plot, what we're meaning is that's where our straight line approximations are going to start happening. In terms of, for a linear factor, we will be at 0 dB for that factor until we reach that break frequency. And that's on our approximation of the straight line asymptotic behavior. And we will go through that with the Goldilocks, and when we're right at the sweet spot, if you really needed to know the exact value of the magnitude, then it's going to be down or up 3 dB for every linear factor you have at that particular break. That's if you were really trying to get a more precise value. And that's only the value due to this single linear factor. If you have a lot that are overlapping in terms of these poles, or if they're close to each other, then you're going to have all of these different factors contributing at certain frequencies. You could also, if you wanted to, you could say, oh, this is 1 over p, or that's 1 over omega naught. That 1 over omega naught is our time constant tau for that particular linear factor. It's just however you want to refer to that pole location or break frequency analytically. Then we have the formula for the magnitude, and this is in dB, and if we assume that we might have capital N linear factors at the same frequency, that's where that capital N is coming from. The positive piece is the zeros, if we had zeros. The negative exponent means that, oh, those are actually coming from the denominator, and those would be poles. The expression, which you could numerically evaluate for any value of omega, would be exactly this value. But we use this expression to figure out what's happening straight line approximation-wise relative to our sort of 3 key frequencies. And that's where the Goldilocks is coming in. We can do the same thing with our phase. We're just looking at the phase of this complex number. That's a linear factor, which really is, all it is a complex number. If we had multiples of those factors at the same frequency, that's what the capital N means, and that just means that we would adjust the angle by however many poles or zeros we had at that particular break frequency. And the angle of this complex number is just the imaginary part over the real part, but since we've normalized the real part to always be 1, we're simply going to have the inverse tangent of this imaginary piece, omega over omega naught. Omega naught is the fixed pole location, or the break frequency. Omega is what is varying. And if I said, what's the angle contributed by the zero factor that has a break frequency at 2, you could use this formula and then say, oh, he wants the angular contribution at 6 radians per second. You would just plug in 6 here, and omega naught, whatever I said that pole or 0 was at 2. You would just have 6 over 2. That 2 would always be fixed, but you could then vary the omega, and that would give you your angular contribution due to that single factor. Questions on the formulas for the magnitude and the phase? If we're okay with that, now we can move into our nursery rhyme, or whatever it is, Goldilocks, and deal with these 3 critical frequencies and evaluate the magnitude and phase at those 3 values that allows us then to sketch or to figure out these straight line approximations for the linear factor. When we say we have a low frequency, that means we are at least a decade below, and a decade is a factor of 10. When we have a high frequency, that's a decade above, which is another factor of 10, and that's then bounding or on either side of the break frequency omega naught. Those are our 3 key frequencies. If we now said, let's look at the low end. Remember what our linear factor looked like. It looked like j omega over omega naught plus 1. If we're saying that this omega over omega naught, which is also omega tau if you write it in terms of the time constant, if that is low, that's really saying that this complex piece is much smaller than 1. That's what we're meaning. Or we're really saying if you plugged in omega equal to 0.1 omega naught, you're saying, oh, a tenth is much less than 1. That's the approximation that we're using. We're saying that 1/10 is much smaller than 1. If this is now 1 plus j 0.1, we're simply going to approximate that by 1. We're going to throw away that imaginary piece, and that's true as long as the frequency omega is a decade below the break frequency. We can now apply that approximation to both cases, the magnitude and the phase. For the magnitude, if we said that the complex number could be approximated by 1, we're now taking the log of that magnitude of 1, and that's 0. We're now saying that that linear factor has a dB of 0 until we get to the break frequency. Well, actually, this is true as long as we are a decade below the break frequency. What we're going to do is we're going to see what's happening below the break frequency, what's happening beyond the break frequency, and then we'll find their intersection with the magnitude, and that's going to be right at the break frequency. The phase, we said the complex number for low values of frequency was 1. The angle of 1 is 0. Those are now our 2 sort of data points for small frequencies omega naught or omega. We can now look at the same scenario if we had high frequencies. For the high frequency case, now we're saying that this omega times the time constant tau, or the omega divided by the break frequency omega naught, is much bigger than 1. Or this is saying that omega is much bigger than omega naught. Now we can look at our complex number for the linear factor, the way that we have now normalized it to be in time constant form. Now we need to look at this expression when we have this situation, when the frequencies are much bigger than the break frequency. And we're going to say that that's when omega is a decade beyond. So what does this look like? This complex number, how can we approximate it, or can we approximate it when this complex, or the imaginary part, is much bigger than the real part? Now we're saying we have 1 plus j10. And we're just going to say, oh, that's basically J10. So this is now J omega over omega naught. And we're saying that that is when we have omega much greater than omega naught, but much greater, we are saying is a decade beyond, that 10 omega naught. Now we can do what we did for the low frequency case. Now we can look at the magnitude and the phase under those approximations. We now have this magnitude of h of j omega. When we're doing the approximation, we now have plus and minus 20 times n log of whatever it was that we said we were approximating it by. Now we have this j omega over omega naught, or we're simply looking at the imaginary part of that. The j doesn't impact our absolute value. This is now approximately plus and minus 20n, and we can break up that division by subtraction since we're doing the logarithm. We have the log of the numerator minus the log of the denominator factor. And that may look a little bit messy until we realize what we're actually sketching. We're sketching the magnitude relative to the logarithm of the frequency. This is now our independent variable, this log of omega. Omega naught, for any given break frequency, this is just a fixed number. And what can we say about this magnitude? If we look at what would happen when omega was equal to omega naught, these two cancel and we're at 0 dB. But once we get bigger than omega naught for our values of omega, this is really like a straight line. You could say this is m, your slope. This is now your x, mx, and then this would give you a constant, your y-intercept in a sense. This is now giving you a sloping line with a slope plus 20n if it's a zero factor, or minus 20n if it's a pole factor. Question? This is now, here is our factor, linear factor, 1 plus j omega over omega naught. We said, let's look at what this looks like when we have high frequencies, when omega is a decade beyond omega naught. If that's the case, this is like 1 plus j10. We're simply approximating that with the j10. This is now what we use to replace that linear factor in our magnitude expression and in our phase expression. That's the omega and the omega naught. So omega naught is fixed. Capital N is how many poles or zeros we have at that break frequency. If we had 2 poles at a break frequency of 5, then capital N would be 2. And we would be sloping at minus 40 dB per decade. So the capital N is the number of poles and zeros. Generically, that will be 1, won't it? You won't have overlapping poles and zeros. But you could have on the test or anywhere else multiple or repeated zeros or pole factors. Pardon? And especially if we have complex poles, we are going to approximate that by 2 real poles at the same location. This is now our expression for the magnitude, and this now produces this straight line behavior, but it's a sloping line. It's not flat. It's now a straight line passing through where you just told me it goes through 0 dB exactly when the frequency omega is at the break frequency. And the slope of that straight line will depend on whether it's a pole or a zero factor and whether you have more than one pole or zero at that location. And if you have more than one, that capital N is going to be bigger than 1. That's now how the magnitude behaves. It was flat, and then right when we hit the break, oh, now it starts looking like a straight line with a slope. And it goes down if it's a pole, and it goes up if it's a zero. On the test, I'm not going to have you give me a more precise value. I want you to simply sketch the approximations for all of the different factors and then add those up and not have to worry about what happens right at the break frequency, which is going to be this adjustment of plus or minus 3 dB. We'll talk about that in just a minute, but for now, let's look at an example. If we now had a single pole that's how we could express that factor for a single pole. And how would we sketch this? Well, what we've just found is, in this case, our omega naught is 25. And we said, oh, well, we're interested in these 3 different frequencies, a decade below and a decade beyond. What we just discovered was that a decade below the break, we were at 0. A decade beyond, we're sloping at minus 20 N dB per decade. And we found that actually we were equal to 0 dB right at the break frequency, and so that's why we're going to just go ahead and connect these straight line approximations for the magnitude. And for this is a single factor, so that's the 1. This is now the magnitude. If we called this h sub x, this is now h sub x in dB. That's its magnitude. That's the straight line approximation for this single factor. If we wanted its phase, again, this is high frequencies. Which says that omega is much bigger than omega naught, or we have 10 omega naught much bigger than omega naught. That's the approximation that we're using. For our linear factor, which we said was h sub 3 of j omega, we are approximating that by plus or minus n j omega over omega naught. If this is now for big frequencies, this is what the phase looks like. And what's the phase of that for all these omegas beyond 10 omega naught? That's just 90 degrees, isn't it? The J. So this is now an angle of plus and minus 90 N degrees. In our example that we were dealing with before, where we had h sub x, was this j omega over 25 plus 1. Now what we can do is, again, we can sketch the 3 frequencies. We found a value of 0 degrees when we were a decade below the break frequency. For a pole, we are a decade beyond, we are at minus 90 degrees, and we are agreeing to simply connect these with a straight line in between those two limiting cases. And it so happens that that straight line will pass through where it's really passing through, which is at minus 45 degrees for every linear factor when we hit the break frequency. And that's coming to us if we simply went through and did this same kind of analysis with that linear factor for medium omegas. Question? It's minus 90 degrees because it's a pole. It's going downstairs. It's in the basement of your transfer function. These pole factors, that's how I would suggest you maybe start thinking about it for now, is we have zero factors and pole factors. The zeros are upstairs, the poles are downstairs. The zeros will give us plus angles and the poles will give us negative angles. And we're going to the ultimate value, and think of that also if you were standing on the pole in the complex S-plane, maybe that pole was at minus 25, and you're watching that frequency go up the imaginary axis, your neck is only going to get to 90 degrees. But since you're standing on a pole, you know that's downstairs and you're subtracting that from your angular contributions. Question? Yes, so if you had two roots at 25, if this was now a minus 2, you had two pole factors with a break of 25, you would now simply enhance or increase this by that factor of 2. You would now be at minus 180 a decade beyond, and that straight line would connect the two extremes, 0 and minus 180, and right at the break you would now have an angle of minus 90 degrees. The linear factors always start at 0 degrees. These linear factors, and if you look at that, it should make sense. If you simply look at this factor, when omega is tiny, just make it really tiny and say 0. Now you're looking at what's the angle of 1. That's 0. And that didn't matter whether it was a plus or a minus, whether it was a 0 or a pole. So you're starting at 0, and then you go down if it's a pole, you go up if it's a 0. So now we'll hopefully get to a point where we can look at multiple different linear factors, and they'll all start kicking in and out at different locations or different frequencies. And you'll have to account for those in aggregate when you're putting together the total phase response or the phase curve. So you'll sketch each of your individual pieces like this, but now when they start all playing together, you have to linearly combine those for each frequency, omega. If you're at the midpoint or the break frequency, we now have particular behavior for this linear factor. We now have this when our frequency omega is right at the break frequency, or when it's omega naught. This now becomes j omega naught over omega naught plus 1, or that becomes j plus 1. We can now look at the magnitude right at that mid frequency, the break frequency. And that's going to be plus and minus 20 capital N log of the magnitude of 1 plus j. Or this is now plus and minus 20n log, and what's the magnitude of 1 plus j? One plus j, we now go one real direction, one imaginary. We now have the hypotenuse, which is the square root of 2 we now have right at the break frequency, this is the magnitude contributed by a pole or zero factor. The square root, since we're dealing with logarithms, that can be converted to 1/2 as an exponent, and that 1/2 can come out front. And what did we say we were going to say this was? That's now that 0.3, the log of 2. And the 1/2 and the 20 can be combined, and we now have plus and minus 10 log of 2, or this is now plus and minus 3n dB, right at the break. If you had two poles at a break frequency of 25, you're going to have then, if they're well separated from everything else, those two factors will actually be analytically right at minus 3 times 2, or minus 6 dB. That will be down from your straight line approximations that we're doing. We can also look at the phase curve. Right at the break frequency, and now we're saying what's the angle of this linear factor that could be repeated, zeros or poles, n times. And now we simply say what's the angle of 1 plus j? That's 45 degrees, isn't it? So this now becomes plus and minus 45 in degrees right at the break frequency, right at omega equal to omega naught. Question? If you wanted to find values of the phase in between these three extremes, you would want to go back to this particular expression and plug in the appropriate omega. If you wanted to now say, oh, I want to know what's happening magnitude and phase-wise right at omega equal 10, you would plug in omega equal to 10, and you would say, okay, this is now a complex number, 1 plus j 10 over 2.5. And you'd say, what's the magnitude of that? Once you found the magnitude, you could just say 20 log of that, and that gives you your dB value. And it would have to be either negative or positive, depending on if it's a pole or a zero. You could also find the angle, or I'm sorry, yes, the angle or the phase of that factor at 10. And you could measure that on a piece of paper, too, if you drew it out correctly on a piece of gridded paper, if you wanted to. Let's look at a very simple example of a linear factor. Suppose somebody now gives you this transfer function. What's the structure, or what's this type of transfer function? Or what form is this in? This is the pole zero form. If we're sketching Bode plots, we really want to create that or transform that into time constant form. We can do that by factoring out the pole from the denominator. And I just so happen to give it a 1,000 in the numerator, and that makes it clean. Now I simply have this 1 over s over 1,000 plus 1. And what exactly is that? If I said, oh, here's a transfer function, 1,000 over s plus 1,000, could you give me a description of what that transfer function represents? That's a low-pass filter. This is simply now a low-pass filter, and with that information, you should be able to anticipate what the Bode plot of that transfer function looks like. You could actually write this out in terms of words. You could say, oh, if I look at that, I'm actually 0 dB until I reach the break frequency. And the break is happening right at 1,000 radians per second. My magnitude is flat now until I reach that break. This is the straight line approximation. Once I've reached the break, then I start sloping. And I'm going down, since it was a pole factor, I'm going down 20 dB per decade after the break frequency. And I just keep going down. I never shut that slope off in the magnitude. That just keeps going and going. Keeps rolling off at 20 dB per decade or 6 dB per octave. If somebody wanted to know less of a frequency difference, they might want you to go in terms of octaves and not decades. What's the phase of this look like? This now, and I just identify the three pieces. It's going to be 0 degrees, a decade before the break, which is happening at 100 radians per second. It's going to be at minus 45, right at the break. And it's going to be then at its ultimate value, minus 90 degrees, a decade beyond that break frequency. Now I've written a verbal description or a written description of the Bode plots. I can now sketch those. My H, if this is now 0 dB, this is now, let's say, minus 20 and minus 40. I need to simply identify some frequencies of interest. Which for the magnitude, I really only have to worry about the break frequency and later. I now know that I'm flat or at 0 dB until I reach the break frequency, which is 1,000, and then I'm going to be going down 20 dB per decade after that. And I like to usually indicate that by saying here's a slope of minus 20 dB per decade. And that's actually a logarithmic horizontal axis, log of omega, but we simply usually label that as omega. Now if we wanted the phase, now it is important to know something a little bit before the break frequency, and in particular a decade before. We're now 0 degrees until we reach a decade before the break. A decade after the break, we're all the way down to minus 90, and in between, we are agreeing that we will just connect those two extremes with a straight line, and we should be passing through minus 45 degrees right at the break frequency. That's what happens with a particular linear factor. Now, if you had 6 of those, you would have to do 6 of these on top of each other and put them all together, put all the pieces together. Yes, sir. correct. So now this red line is just the contribution due to this single factor. And if you now had another factor, let's say you had a 0 that was at 5. Now it's break, oh no, let's not do 5. Let's say 500. Now this would be its break frequency, a little bit below 1,000. We would have to go back a decade before, and now the 0 would be kicking in at 50. And it would turn off at 5,000. Meaning, after you've reached 10,000, you have minus 90 and plus 90, you will be at 0 degrees. Getting there, you will first bend up, then they will both be sloping at the same amount. You'll go flat until your 0 quits. Your 0 will quit contributing a slope at 500, or I'm sorry, at 5,000. Then the only thing sloping is the pole. It will bring you down to 0 and you'll go back. And that's now what your total phase response would look like for two factors, two linear factors. So I would suggest the question was, will we get partial credit? And the easy answer is no, but the right answer is yes, you will. If you draw all of your individual pieces and then you mess up combining those, at least if your individual pieces have been drawn accurately, you'll get credit for those pieces that you've drawn accurately. Now, you may not get full credit if you start adding them up wrong, but you will get some credit for showing me, oh, they know where the break is, and these phases are split between the two endpoints of 2 decades around the break, etc. Question? So what does it mean for a transfer function to give you 0 degrees phase? What does that mean, or how can you maybe be thinking of that? In this particular case, you know what should be happening. This is now a low-pass filter. That means you should be passing frequencies below 1,000 radians per second. Well, even below 100, what it's saying is they will basically be pretty much aligned in time. The output won't be behind or lagging because the phase angle is 0 degrees. This gives you the phase change as your signal goes through your system. This gives you the way that your system adjusts the phase angle of your input signal or input waveform. If you now have an angle of 0 degrees, that means that they're locked on in terms of one is aligned in time with the other. The input is aligned with the output. If you now come over here and say, oh, right at 1,000 radians per second, my magnitude actually will be 3 dB down, so you're now at a half power of where you were with the input, and your angle, you're now shifted in time by whatever 45 degrees represents in a frequency of 1,000. But it is a phase shift. So your output is now lagging behind your input. And it may or may not be a good thing or a bad thing to have a phase shift. It depends on what you're trying to do. If you're trying to model a communication channel, and you know that your communications channel impacts your signal, transmitted signal in this way, then at your receiver you can maybe add in or take away or account for that delay in time or that phase shift. Same if you had any other system, if you know it's there, then that's to your advantage. And that's what we're trying to understand, is how to model this. Question? Oh, if I had in this transfer function, instead of 1,000, if I started with 10,000 in the numerator and I kept my pole at 1,000, what's that going to do now? How does that change my phase plot? It doesn't change my phase plot at all, does it? But it does change my gain plot or my magnitude plot. I now have 10 for my overall gain. Meaning, you could now go down to your gain plot and say, oh, I have actually a gain of 10 in addition to this red line. And what's a gain of 10? 20 log of 10, 20 log of 1, that's 20 dB. I can now just everywhere shift this 20 dB up. Or you could erase this and say this is plus 20, this is 0, and this is minus, and it's the same thing. Is that clear? So you've just shifted your gain or your magnitude plot up by 20 dB with an increased gain of 10. Well, it may not be a DC offset. Usually when you're talking about an offset, you're thinking of a signal that might have a DC offset added to some waveform. This is now a system. So this system would amplify your waveform or your signal consistently for all frequencies by 20 dB, or a factor of 10, if you now have a gain of 10. It's not so much a DC offset, but it is a gain adjustment. It is how every frequency is adjusted as it moves through that system. Let's look at another example in terms of characteristics. Suppose I give you, and this is what I'm hoping you're starting to get out of this discussion. Maybe you're bored by Bode plots, but what I'm trying to do is make you marketable. I went home last night, or I was listening to the radio, and they said, oh, we don't want just monofocused, basically, engineers. We want people that can see the big picture and that can solve problems. I don't know. But irrespective of what station that was, this is now, I want you to start thinking about what does it mean if somebody gives me this transfer function, or can I think my way around this without having to just, wait a minute, give me 10 minutes and I'll sketch the Bode plot. Can you start to infer certain characteristics or properties of this particular transfer function? And that's what you want to be doing when you're thinking about these Bode plots, because it wouldn't take too much for somebody to learn how to plot this in MATLAB. They wouldn't pay you the big bucks to just plot this in MATLAB, would they? They would pay you the big bucks to figure out, is this what I need? Is this the system that I have? And how do I change it or make it different if it's not what I want? You see the big picture. Meaning, what are some generic characteristics associated with this transfer function? For example, on the exam, I could ask you, what is the phase of this system, let's say of G of S, at low frequencies? That's a fairly general characteristic of this system. What's the phase of G of S at low frequencies? And what's the first thing you might have to be thinking about? What's low? You're thinking of frequency response, aren't you? You're thinking now, and when you see this, you should be starting to see this many different ways. You might already see the Bode plot, magnitude. You might see the pole zero diagram. Did anybody see the pole zero diagram? How many poles do you have? How many zeros do you have? Finite zeros. 0. You have 2 X's, don't you? Is this a BIBO stable system? How many say no? How many say yes? How many are not changing? So they're not filtering their answer, right? Where are your poles? Right at the origin and at minus 0.2. You have one that's good, minus 0.2. You have one that's right on the boundary of stability, and that's not a BIBO stable system. Because what could you hit this with as far as an input signal, a bounded input signal that would cause your output to go unbounded? Any constant. All you have to do is add a signal that has a pole at the origin. Any constant will drive this system unbounded. So a bounded input would be a constant, and that would cause an unbounded output. That still hasn't answered this, so I guess we're buying time with the interviewer. The interviewer is giving you this transfer function, and he's saying, all right, what's the phase at low frequencies? First off, you might have to tell the interviewer what you're assuming low frequencies are. What are low frequencies in this case? We have something that's happening at DC, aren't we? So that's really low. We have something happening at the origin. We have a pole at the origin. So now let's see, what's our next lowest frequency? Now it's 0.2. Well, maybe we go a decade before that, and we say, oh, that's 0.02. So I'm considering low frequencies to be something less than 0.02. If I now said, what's the phase of this below 0.02? Well, now you could even plug that into your calculator, but now maybe you don't have your calculator at the interview. You may not be carrying that in your pocket or on your belt or wherever we carry it. So what is the phase at low frequency? We have a pole at the origin. That pole is always giving us minus 90 degrees, isn't it? What's the phase at high frequencies? Now we have two poles that have kicked in. We didn't have any zeros contributing phase, and now we have minus 180. What's that do to a signal? If you pass a signal, a high frequency signal, into this system, what's its phase doing? It inverts it, doesn't it? So if you had now a waveform that was going up, down, now your output is going down, up, down, up, down, up. You have a phase inversion, a 180 degrees phase. So now this is going to be this shift of 180 degrees. What are some other questions that I might ask you? I might say, and these are quick answer, what's the gain at DC? What's the DC gain of this system? And these are quick answers on the exam. What's your DC gain? What's DC? 0, right? So now if I plug in S equal to 0, what's happening? It's not very well behaved, is it? And what's the Bode plot of this doing at low frequencies? The Bode plot. What's this guy? This is a pole at the origin. What's its Bode plot? That's just a straight line, and it's always minus 20, isn't it? If we just had that and nothing else, we could pin that down. How could we pin it down? It's always sloping. We would just identify the omega equal 1 frequency, and what would the magnitude be at omega equal to 1? If all we had was 1 over S and nothing else, what would its magnitude be? Nothing else. We don't have anything else. We just have 1 over S now. It would be 1, but in dB, that's 0, isn't it? 20 log of 1 is 0. We now have this sloping line, and what's it doing at low frequencies? It just keeps growing and growing, getting bigger and bigger. And the phase we know is minus 90 for low frequencies. If you now had this question on the exam, you might just say, well, this is actually, for this particular problem, the DC gain is undefined or it's infinite. Now, what's another question I might ask you? I might ask, what's the slope of the magnitude at low frequencies. What's the slope of this? Now we're anticipating these characteristics before we even sketch the Bode plot, so that we, what? This is basically, we're going to the back of the book and finding the answer in the back so that we know what to expect for our answer. That's what these characteristics are telling us. We know that the phase needs to start at minus 90, needs to end at minus 180. You could draw that almost immediately. And then you just have to find these frequencies of interest. We also know the gain curve is, at least initially, it's going to be really big and it's coming down at 20 dB per decade. Whoops, shoot. What's the slope of the transfer function at low frequencies? I just answered it, didn't I? Minus 20 dB per decade because of that pole at the origin. What's the slope of our magnitude at high frequencies? Now we just have two poles, don't we? We don't have any zeros. If we had zeros, they would be adding some slope at the positive piece, but now we just have two pole factors. And though each of those linear factors contributes 40 dB or 20 dB, we have two of those. Our slope now at high frequencies is minus 40. Now with a few quick answers, I've asked you a fair amount about that transfer function. You know it has an infinite gain at DC, it has a phase of minus 90 at low frequencies, it has a phase of minus 180 at high frequencies. It's sloping at 20 dB per decade until when? When does it transition between these two slopes in a straight line approximation? At what frequency? At 0.2, right? So now you would find 0.2 on your scale, and where would that be? 0.2. That would be 30% of the distance between 0.1, or 10 to the minus 1, and 1, 10 to the 0. So you're 30% of the distance, linear distance, on this logarithmic axis, and that's where you would be breaking. You would be changing your slope. You would be going minus 20, now you're doubling it, you're now minus 40. Questions on linear factors? Yes? The question, I think, was, is this a better or worse low-pass filter? Is this really a low-pass filter? You may not even want to consider it a low-pass filter because you now have infinite gain at DC. Meaning you're going to, if you hit it with a constant, you're going to go unbounded with the response, and that's maybe not low pass in behavior. I think what you were wanting to maybe ask is if we erase that pole at the origin and maybe we squared this. We had two factors at 0.2. Now it's up to you to decide for your situation, is that a better low pass filtering behavior than another? And we may say, well, it's maybe giving us faster attenuation into the stop band, but maybe we don't like the way it rolls off into that stop band, and we'll start designing Butterworth filters after the exam, and we'll see that they have a better magnitude response in the pass band. Is this transfer function good for anything? Well, this actually might be modeling a DC motor. This might be an electromechanical systems transfer function, where you might be injecting or applying a voltage, and this is now spinning. And if you now apply some voltage, you now may just spin at a nominal velocity or a nominal RPM. And this might be modeling a DC motor. And you may or may not like its behavior. Let's now see if we can talk a little bit. I mean, these are good questions. You can see that we could be here all day, right, with just Bode plots. And we just talked about one linear factor or two or a few roots. Let's look at the complex factor. Here, what I'm wanting us to focus on is something like s squared plus 12s plus 900. And we're comparing this with this s squared plus 2 zeta omega sub n s plus omega sub n squared. Now, is this a complex factor? Does this have complex roots? I might give you a second order polynomial, and it may just be two linear factors that are multiplied together. You need to figure out. So don't forget what you probably learned many, many years ago, maybe in preschool, your quadratic formula. I'm not sure where you learn these things anymore. If we had this as squared plus bs plus c, the reason I'm going over this is because on the exam, a lot of times people just see a second order and they just assume that it's quadratic or that it's complex roots, and it may not be. So don't assume, even though I'm maybe giving it to you in a quadratic form. What's the quadratic formula? Now we have this negative b plus and minus the square root of b squared minus 4ac over 2a. When does this give rise to complex roots? When that argument under the radical is negative. If you now take b, square it, and subtract 4ac, and if that gives you a negative number, then you've got complex roots. Then you can use what we're just talking about. If you get real value, or a positive value for b squared minus 4ac, so we're now looking for b squared minus 4ac less than 0, then if this is less than 0, we have the complex roots case. For this example, we have a equal 1, b equal 12, and c equal 900, where we now have b squared minus 4ac, which is something that's negative. So this is actually going to be complex roots, right? And in fact, if we now looked at this, the natural frequency squared is 900, or what is the frequency associated with this complex factor? It's the square root of 900, or now we have a pole or two poles that are 30 radians per second away from the origin. Where they are located on this arc that's 30 away depends on the value of zeta, which if we look at this, we now said that 12 was our b, and that's 2 zeta omega sub n. We just calculated omega sub n to be 30. We can now say that zeta is 12 divided by 2 times 30, or 6 over 30, or 1/5, or 0.2. When we have a complex factor, that damping ratio zeta is going to be living between 0 and 1. For values of zeta between 0 and 1, we have complex factors. And what we want to do now is look at the two different extremes. We want to look at what happens when zeta is 1 and what happens when zeta is 0. We want to look at those two extremes, and then we're going to use the one extreme, which is the zeta equal 1 value. our two extremes. Let's look at the first one, the easy, or maybe the cleanest one, which is what we're going to do. Let's say zeta is equal to 1. Now we have s squared plus 2 zeta, which is 1, omega sub n s plus omega sub n squared. But that's a pure square, isn't it? This is now s squared plus 2as plus a squared. This is now simply s plus omega sub n quantity squared, and that corresponds to 2 real equal roots. And now you can sketch those. If we had this factor as poles, our break frequency is omega sub n, and our slope is a result of those two, meaning if we were in the complex S-plane, we now have these two poles right here at a frequency of omega equal omega sub n, and this is now zeta is equal to 1. That's the picture in the complex S-plane. And what's the phase look like for zeta equal to 1? Where are we starting our phase? 0. Where are we ending our phase? Minus 180. And where are we living between those? Well, we're a decade below and a decade after, and I've called this omega sub n, so let me call this omega sub n. Our phase plot now is 0, and then it's minus 180, and in between, we're this straight line. That's now what it looks like at one extreme, when zeta is equal to 1. Now we want to look at the other extreme, which is zeta going towards 0, and when zeta is actually equal to 0. If we now look at the other extreme, when zeta is equal to 0, now we have s squared plus 2 zeta, but we're saying zeta is 0, omega sub n s plus omega sub n squared. What does this reduce down to as a polynomial? Where are the roots of that? Those are now purely imaginary, aren't they? Meaning if we were in the S-plane, now instead of being on the real axis in the negative S-plane, now we're right on the imaginary axis. This is with zeta equal to 0, and they're purely imaginary. What's the magnitude plot look like if we had poles? Let's say this is now omega sub n. And let's say this is now 0 dB, and this is the magnitude of h when zeta is equal to 0. What's the magnitude of if we now have this frequency being low, and this is now downstairs, we now have 0 dB for our magnitude, because we've actually, well, we've normalized this so that we now have s over omega sub n quantity squared plus 1. And when omega is small, we now have just 1 for our gain, and it has a dB value of 0. What happens at high frequencies? And again, we could be marching along this particular axis. Once we get really, really high, this is going to be dominating our behavior. And what's happening? Now we have a slope of twice minus 20, don't we? So we now have 40 dB per decade for our slope. So for high frequencies, we're out here. With the same slope that we had before. What happens right at the sweet spot, or right at the natural frequency? If we were walking under this big top tent, and these represent infinitely tall poles that are used to overstretch this tarp or this rubber sheet, what happens when we get close to that pole, to the height of that big top tent? It's going to be really, really high, isn't it? So our magnitude is going to go up. And in fact, when we get right here, it's infinitely tall, isn't it? So the magnitude goes unbounded. And we now have something like this. This is the one extreme when we're right on the imaginary axis, and the other one was flat and there when we had pure real roots. We are going to just go ahead and approximate all of these as if zeta is equal to 1 for this class, knowing that that's a bad approximation if zeta is small. But we want to just be able to sketch these and know how they're contributing. Question? No. So if it has complex poles for this class, what I'm saying is we can approximate this complex factor by letting zeta, it's between 0 and 1. Let's just let it 1. Let's let it equal to 1. So we're agreeing that for this class, we can simply let zeta be 1. We're rotating those poles. We're keeping them the same distance away from the origin. We're just making them 2 real equal roots. Question? Pardon? That means that we're at the maximum damping for that particular frequency, for that factor. Meaning, if you ended up with something like this on the exam, s squared plus 2 zeta omega sub n s plus omega sub n squared, you can now say, oh, I'm going to approximate that. That's what Tharp said we could do. I'm going to just say approximate with zeta equal to 1. And that now allows you to say, oh, this is s squared plus 2 omega sub n s plus omega sub n squared, or 2 real equal roots. What does the phase look like for zeta equal to 0? Go back to what you know. You know it starts at 0, don't you? And where is it going to end up for poles? Let's say we had 2 poles. It's now going to end up at minus 180. And where does it end up there? Well, we've agreed that that's, 10 omega sub n. Let's say this is omega sub n, and this is now 0.1 omega sub n. We now know that it's here, and it's here. What happens with zeta equal to 0? If you were marching up this axis, and you said, okay, I'm right here, what's the phase? Now you need to say, oh, this guy is giving me 90 degrees, isn't he? This guy is giving me the opposite 90, so they're canceling each other out. I'm at 0 degrees. But what happens when I get right on the other side of that pole? Now they both give me 90 degrees, and since they're poles, they're minus, meaning I'm 0 degrees all the way up until there, and then I'm instantly down to minus 180. That's now the phase curve for zeta equals 0. And we're throwing that away. We're approximating that and saying, oh, well, let's just do it this way. Let's connect it with a straight line. We're assuming they're not purely on the imaginary axis. And even if they are, we're saying go ahead and make the approximation. But this is what it would do. And so you can see that for zetas between 1 and 0, you're simply having a phase transition in between those extreme cases. We'll pick up somewhere after the exam. There is a review session tonight at 5:15 in room 530.